All right, stoichiometry. Stoichiometry, very important method, calculating method to be able to tell different quantities in a balanced chemical reaction equation. It's a way of calculating how much of each chemical species is going to be in there and going to be reacted. Or produced, can also be produced. Okay, so the learning targets here for stoichiometry. I can explain how chemical equations support the law of conservation of mass. I can identify a mole ratio using a balanced equation. This is very important. Very, very important one right here. Mole ratio. I can perform stoichiometric calculations with mass, liters, and particles. So we're going to go back over Avogadro's number, the 22.4 liters, the molar mass stuff. And I can calculate percent yield. Probably I'm going to get to percent yield today, but we will continue on Thursday. All right, so what is stoichiometry? The study of quantitative, so this is numerical, quantity, quantitative, has the N in it, we know it's numerical data, numerical stuff, between the amounts of the reactants used and the products formed. So we're going to be going from reactants to products, products to reactants, reactant to reactant, or product to product. We're going to be able to hop around our chemical equation, our balanced reaction. Stoichiometry is based on the law of conservation of mass. The law of conservation of mass, of course, tells you that matter is not created or destroyed. So however much you start with in the reactants is how much you should end with in the products. Now it can change form. It can be in a new compound. It can be in a new deal here. But the masses of each element on each side should remain the same. Chemical bonds in the reactants are going to break. New chemical bonds will form to produce the new substances or the products. But the amount of matter present should remain the same from the beginning to the end of the reaction. However much you start with, it should be however much is also at the end when you add it up. And we're going to prove it. We're going to check out this law of conservation of mass and prove it mathematically and see how that works. But the matter present at the end of the reaction is the same as it was at the beginning. Therefore, the mass of the reactants equals the mass of the products. Mass of the reactants equals the mass of the products. And that's what we're going to do, is we're going to prove this mathematically. Check it out. See how this works. We're going to start with looking at an equation, looking at a reaction. We're going to look at it from all aspects. The word equation, the types of stuff in there. Then we're going to talk about the mole ratio. All right, so here, relationship derived from a balanced chemical equation. The top part there is the word equation. We have iron, which is a solid metal, reacting with oxygen gas, which is 19% of air. So it's pretty accessible reactant at all times, is going to form iron 3 oxide. Now, iron 3 oxide is rust. It's that reddish stuff, that you see on metals and things. Now, if you were to write out the formulas, write it out from the word equation, and balance it, you would get 4 irons, 3 oxygens, 2 of the iron 3 oxide rusts. But what does that really mean? What does it mean in terms of words? Technically, When we say 4 Fe, we're talking about 4 iron atoms, okay? 4 iron atoms. Because iron happens to be an element, it's monatomic, it's singular, so it's just atoms of iron. O2, though, happens to be a molecule. It's labeled as a molecule because it has that covalent bond, it shares electrons. So, because it's diatomic, it is a molecule. And then over here, the iron 3 oxide is actually an ionic compound. So 2 formula units. Remember, formula units is the word we use to describe ionic compounds. It's the lowest ratio of the different ions in that ionic compound. But that's a lot to deal with. Atoms, molecules, formula units, they're all different terms, right? So instead of identifying them that way, we're just going to use the counting unit mole. Okay, and that's why we switched to this mole. It's a counting unit. It's the same for everything. Here we have 4 moles of iron. Okay, technically it's 4 atoms of iron, but we're just going to call it, that's 4 moles. Over here, 3 moles of oxygen, or O2. And then 2 moles of the iron 3 oxide. So 4 moles is needed to react with 3 moles of oxygen to get 2 moles of our product here. And this is the mole ratio. So 4 to 3, 4 moles of iron to 3 moles of oxygen. It's like 4 parts to 3 parts here. If we're talking about the moles of the iron to the moles of the iron 3 oxide, now it's 4 parts to 2 parts. 4 moles to 2 moles. Okay? So just think of them as parts, think of moles, it's just a count. I need 4 of these iron things, I need 3 of these oxygen things, and that's going to give me 2 of these combined iron 3 oxide things. So now we're going to prove the law of conservation of mass and how it works. Hi, how are you?
Doing fine. Did you see that email about?
Law of conservation of mass here. We're going to prove it, starting with our moles, our counts here. So if I have 4 moles of iron here, I'm going to change that over to mass. How do we change moles to mass? How do we convert that? What do we need to use? The grams part, what is that called though? Where do we look and find it? That grams part. Yes, we're going to mass. So moles of Fe, 1 mole of Fe equals how many grams of Fe? What do we call that? 1 mole of any substance equals this many grams. That's going to be the molar mass. And I look for it on the periodic table. Now, if I look at the periodic table, I want everybody to do their molar masses to 2 decimal places so we get the same molar masses for everybody. So what is the molar mass of iron on the periodic table? What does it say up there? Or what does it say on yours? Iron somewhere in the middle, the transition section. What is the molar mass? What do we got here, guys?
55.847.
Okay, so 2 decimal places. We're going to do 55.85, 2 decimal places for all these molar masses. So let's go ahead and calculate that. The moles are going to cancel with the moles. Now for our purposes, since we're dealing with molar masses, I'm just going to carry it out 2 decimal places. So this is going to be okay, so this is 223.40, correct? 4 times 55.85 over 1. Okay? So that's my first one. Now let's do the second one. We're going to do oxygen here. So we have 3 moles of oxygen. So we diagonal down our moles of oxygen. They go down here. So 1 mole of oxygen equals how many grams of oxygen? What is the molar mass of oxygen on the periodic table? Round it to 2 decimal places, please. 2 decimal places.
16.00.
So 16.00, however, oxygen is diatomic, so we need to multiply it by 2. So 16 times the 2 here gives us 32. Now let's calculate that. What is 3 times 32 divided by 1? 96 grams O2. So far, so good. Now we need to calculate the last part in our equation. Remember, moles cancel with moles here, and so then we're left with the grams. Last part over here, we get 2 moles of the iron 3 oxide. Okay, so the moles of the iron 3 oxide, that equals how many grams? Now I need to calculate molar mass. I have 2 Fe, so that's going to be 2 times the 55.85. And I have 3 oxygens, and that's going to be, I know that looks like 30, but it's oxygen, 3 times 16. I got to add all this up. What do we get for our molar mass here for the iron 3 oxide? So let's get out those calculators. 2 times 55.85 plus the 3 times the 16. So what is our molar mass of that? Anyone? Everybody still there? Anyone? Thank you. Yes, it is 159.7. And so these moles will cancel. We're left with the grams. So multiply that by 2. 159.7 times 2 divided by 1. So this is going to give us 319.40 grams. Fe2O3. Now this one's the product, right? Product. This one is a reactant. And this one is one of the reactants, right? So far, so good. You follow me? We've got the 2 reactant masses. We've got the product mass. Now, according to the law of conservation of mass, what should they do? What should the reactant mass and the product mass do? Yes, it should be equal. Exactly right. Try it. Add them up. Take these 2, add these up. Do they equal our 13, or I mean not 13, our 319.4? Yes, they do. So as you can see, we mathematically proved that mass is being conserved here. That nothing's being created, nothing's being destroyed. It actually goes in there together, right? Yes? Good? So far follow me. Okay, because it's going to get more complicated. But just let's go ahead, show it one more time. The 4 moles of iron. Okay, change that over to grams using the molar mass. This is in the PowerPoint, so if you need to go back and look at it, you can pull it up and watch the addition of the stuff. Okay, we diagonal it down, we cross it out, we multiply, we convert it, and we get that. We do the other reactant, just like we just did, and we convert it, 96, and then we do the product. 2 moles, change it over to mass, and we get that 319.4. Now, all we have to do is add the reactants, okay? Add those two together, and you should see that they are the same value. And this is why we can do that mole ratio, and we can say 4 of these things are equivalent to 3 of those things, which are equivalent to 2 of those things. And those things that I'm talking about are the moles, okay? Mass of the reactants equals the mass of the products. All right, now, we've done mole maps and other conversion charts. This one is going to help you follow what you need to do and in which order. Because you're always starting with one of the chemical species in the chemical reaction, and you're always going to be working to another chemical species in the chemical reaction. So the one that they give you the number on, the given number, that's going to be your A substance, the given substance. The one that you're trying to find, the other chemical species, that's going to be your B substance. So, now it depends on what you start with as to how many steps it's going to take. If they start you off with particles, grams, or liters, you have to do a conversion first before you can switch and do the mole ratio. If they start you off here at moles, you get to skip this part and you can just keep going. It really does depend on where you start and where you need to work to as to how many steps it's going to take. Now there's this generalized map for you, and I put it in the notes, but I also gave you this one to help you remember all the conversions. Because remember, converting for particles, that uses Avogadro's number, the 6.02 times 10 to the 23rd. And remember the common particle names, atoms, formula units, molecules, and then sometimes ions. If you see any of those, you're going to have to use Avogadro's number and convert it to moles first. The one for gases at standard temperature pressure is 22.4 liters. So I put this in here. So if you start with liters, you need to change it to moles. Got to use that 22.4. And then last but not least, if you have grams to start with, you use the molar mass off the periodic table. Now they could start you off with one of those and you have to convert to moles first, but they could always ask for those in the end. So the substance B over here, you could have to convert at the end to get the correct measurement value, whatever unit they want, particles, grams, or liters. So we're going to work through a couple different types of problems. We're going to start with the easier ones that only take 1 step, then we'll move into the 2-step ones, and then we'll move into the 3-step ones. Okay? So let's look at the mole to mole. This one is the easiest, it really is. So 1 step. Mole to mole, because we don't have to convert with the grams, the liters, or the particles, because we're just sticking with moles here. Now this reaction, we have ethane, 2 moles of ethane, 7 moles of oxygen. Those are reacting to form 4 moles of carbon dioxide and 6 moles of water. So don't forget that 2 to 7 to 4 to 6, those coefficient numbers are important. Now let's take a look here. To produce 12 moles of water, so that goes over here. We're going to have 12 moles of water. How many moles of oxygen are needed? How many moles of oxygen are needed? Well, the one that we're starting with is the A value, the 12 moles. This is your A, substance A on the chart. This is your substance B. This is what you're working to. Okay? So I'm looking at the water to find out how much oxygen was needed to begin with. So I always start with my given, and that one's the one that goes in the upper left corner of my T-chart. And you must make sure you write down the substance. The substance is important because we're going to switch it to the other substance. So you have to put the water in there in the T-chart. Now, I have to go from the water over here to the oxygen. That means I don't need to care about the carbon dioxide or the ethane. Neither one of those affect this problem at all because I'm not looking for them. So I'm just going from water to oxygen. So I'm going to take this moles of water and diagonal it down. I put the moles of water on the bottom here. And because I know that this is a balanced reaction, and these two chemical species are both involved, I can go between them. This is the mole ratio. So I have, this is called the mole ratio. In the balanced reaction, I have 6 moles, because of the coefficient of 6 in front of it. I have 6 moles of the water, okay? I have 7 moles of the oxygen. So I'm using the coefficients in the balanced reaction to establish the mole ratio. Now this is really just multiplying a fraction. I have 12 times 7 over 6. That's basically what I have going on there. 12 times 7 over 6. So let's go ahead and calculate that. 12 times 7 divided by 6. So that gives me a calculator value of 14. And if we're canceling correctly, moles of water cancel, and we're left with moles of oxygen. So I need to put those over here. This is the unit, this is the substance. Now, we do have to consider significant figures because we started with 2 digits. The 1 and the 2, that means we can only have 2 digits in our answer. And guess what? We have 1 and 4. It's already got 2 digits, so we don't have to do anything to it. So this would be your final answer here. So 12 moles of water are produced when you react 14 moles of the oxygen. Mole to mole is only going to take you 1 step because all you have to do is the mole ratio. You don't have to do any other converting. So let's run through this one more time before we get on to the 2-stepper. 12 moles to how many moles? We don't need the other 2 substances here. Following our little map, we're starting with the moles of A, which is going to be the moles of the water. We're going to the moles of B, right there. Don't need the other side. So really, of our flow chart, we just need moles of A to moles of B. Okay, so moles of water to moles of oxygen. Insert your T-chart. Diagonal down. Put in the mole ratio. 6 to 7. Multiply 12 times 7, divide by 6. Cancel, and get your 14 moles. Mole ratio, you can just use the coefficients in the balanced reaction, and you can calculate. Now I could calculate the 2 moles of the ethane to the 7 moles of oxygen if I want. I can pretty much do any of them in there if I just know the quantity of one substance. All right, let's look at this one. Mole to mass. Now, technically, you could do mole to mass, you could do moles to liters, you could do moles to particles, or you could do particles to moles, mass to moles, liters to moles. When it's moles to something or something to moles, it's always going to take 2 steps, 2 conversion steps. One's the mole ratio, the other one's the conversion. So let's take a look here. Read our reaction. We have One of the main components of pearls is calcium carbonate. If pearls are put in acidic solution, they dissolve according to the equation below. How many grams of calcium carbonate can be dissolved in 0.0250 moles of hydrochloric acid? All right, so if I'm focusing on here, looking at this, it says how many grams of calcium carbonate can be dissolved in 0.02 moles hydrochloric acid. So I have 0.0250 moles here. And this is the one that I'm trying to find, but I'm trying to find grams this time. So my question mark with my grams there. That means I don't need any of these other ones. They are not a part of my problem. I'm focusing on the calcium carbonate and hydrochloric acid. Now my given information, this is substance A. So this is going to be substance B here. I always put the given one in the upper left corner to start my T-chart. So that's what I'm going to do. Write the mole and the HCl in there, unit substance. Now, I can't go directly from the moles of this to grams of the other substance. But what I can do is go from moles of HCl to moles of the calcium carbonate, because I can use the balanced equation and use the mole ratio. So that's what I'm going to do. I'm going to take these moles, put them down here, the moles of the HCl, and the one I'm trying to get to, the calcium carbonate, I'm going to put the moles up here. This is definitely going to be your mole ratio step. Switching compounds using the balanced equations, this is a 2. So we put the 2 next to the HCl. This is an understood 1. So we put the 1 here. I switched compounds using the mole ratio, the coefficients of the balanced reaction. Great. But I don't want moles of calcium carbonate. I want grams of calcium carbonate. So I have to go one step further. So I add another one to my chart. Guess what I can do? I can take my moles here of the calcium carbonate. I can put them down here, cancel them out, and I can convert to grams of calcium carbonate. All I need is my periodic table and a molar mass. So this step right here is a conversion. We're just converting it from moles to grams. So 1 mole of calcium carbonate equals how many grams? Now I need my periodic table. Calcium is 40.08. Carbon is 12.01. If you look at your periodic table. And oxygen, there's 3 of them and they are 16 each. So go ahead and take a moment and add that up to get your molar mass of calcium carbonate. And yes, you'll get better and more familiar with the periodic table and where to find them. But if you use them all the time like I do, you just have them memorized. So what is our molar mass here of our calcium carbonate? That is correct. 100.09 is correct. So 100.09 grams equals 1 mole. So we have the 2 steps here. We have the mole ratio to switch to the new compound using the balanced reaction. And then we just have to convert at the end to grams. So you're adding in that mole conversion at the end. Now it's like multiplying fractions here. So multiply, multiply. Multiply everything on the top, divided by 2. What do we get for our overall value? So when I type this in, this is how I do it in my graphing calculator. I do 0.025 times 100.09, and then I hit the enter button, and then I do divided by 2. The ones don't really matter. Now, significant digits. Starting over here, these zeros do not count. Remember, zeros preceding non-zeros don't count. So this one actually has 1, 2, 3 significant digits in it. That means I need to keep 3 in my answer. So if I'm looking at my answer here, which is 1.2511, I'm going to keep the 1, keep the 2. The 5 is the one I look for rounding. Do I round it up or leave it a 5? So this one's just going to end up being 1.25 grams CaCO3. Now you can check to make sure everything cancels appropriately. Moles HCl cancel with moles of HCl. Moles of calcium carbonate cancel with moles of calcium carbonate. And then grams calcium carbonate, check, that's what we want. So really all you're doing there is just like multiplying the fractions, just like so. This is a two-stepper. Two-steppers are always going to have one conversion and one mole ratio in it. The one-steppers only just have the mole ratio in it. And then, of course, the 3 ones, which we're going to get to next class, are going to have a conversion, a mole ratio, and another conversion. So let's review this one more time. Give everybody a second to process. Okay. We got our 0.0250 moles of our HCl. We're looking for grams of the calcium carbonate. Okay, we don't need the other 3. It's not a part of this particular problem. So if we look at the little chart to follow, what are we starting with? Well, we're starting with the moles of A, which happen to be the HCl here. Where are we going? We're going to the grams of B. So that means I have two steps here, one here and one here. Mole ratio changed to grams, so the conversion step. All right, so set it up. I got to go to the moles, then I got to go to the grams. T-chart, there you go. Set up your dimensions to cancel, so moles of HCl go on the bottom. Now we have to do the mole ratio. We have 1 to 2 in our balanced reaction up there. So the 2 goes on the bottom next to the HCl. The 1 goes on the top next to the calcium carbonate. Then to do the second one, 1 mole equals the molar mass of the substance, so all we need is the periodic table. Look up the molar mass of CaCO3, 1 calcium, 1 carbon, 3 oxygens, add it up. 2 decimal places off the periodic table for those molar masses. Check and make sure everything cancels, like it does. And look for significant digits. There's 3 significant digits in our initial measurement, the 0.0250. So we keep 3 in the end. And that is going to be the end of the problem.